Hello everybody, today I want to talk about harmonics and filters in the power system. I would like to give you a couple of typical examples for sources of harmonics. Here you have a typical 12 pulse converter as they are used for HVDC. So you see that typically here when you measure the current, this is what you can see in green. This current has harmonics, this is the harmonics measurement. And you see the 50 Hertz, the base frequency. But then you see here the two spikes here. This is the 11th and 13th harmonics, which represent 550 and 650 Hertz for a 50 Hertz signal. Here you have another example, a heavily saturated transformer. Typically in this case you have the base frequency 50 Hertz, and then you have the third harmonics and the fifth harmonics, which is very high, very pronounced. Here I have changed the transformers from a star-star connection to a star-delta connection, and you can see how such a transformer helps to suppress the third harmonics, which you can see here. So I switch on the transformer and you can see that the harmonics, the third harmonics, is reduced by at least 50%. Here is another example with a very simple IGBT inverter. It is a layout with a 5000 Hertz modulated pulse code modulated signal, and you can see here these 5000 Hertz. In reality you would go much higher with the frequency, and you would also choose another layout of the electronics in order to reduce the harmonics from the beginning. I want to demonstrate how we can build close to any shape of current and voltage based on a series of superimposed harmonics. Here is an example. This is a rectangular wave shape, and you can see here at the harmonic analyzer, this is the base frequency 50 Hertz. This is the base frequency, and then we have the third harmonic, we have the fifth harmonic, the seventh and the ninth harmonics, and all the rest I let be. From the frequency analyzer I noted down the first four harmonics. You can see it here. This is for 50 Hertz, it is 127 volts, then 42, and so on. You can read yourself. And now I will build the model accordingly. So I have now built 5 voltage sources superposed on each other. So you can see the individual voltage sources I have added the inputs as I got them from the frequency analysis. So for the base frequency 50 Hertz is 127 volts. The second one is 42.4 volts for 150 Hertz, and so on. So I let it run now and compare the original square rectangle here with what I get with only 4 of the many harmonic frequencies I had in the frequency analysis. You see this is now the total sum, and it looks pretty okay already. I had to play with the phase angle of the frequency, so if I change the phase angle you can see that I completely change also the wave shape. So this was a little bit try and error. Now I would like to demonstrate the impact of harmonics on a distribution grid. This is a very simple distribution grid. Here we have the power source of the distribution grid. It has a short circuit capability of around about 10 kiloamps. Here we have a load, partially reactive. Here we have a reactive power compensation, and here we have the harmonic source. It is a converter. Instead of a series connection of voltage sources with different harmonic frequencies, I have chosen to go for a parallel connection of current sources, but the effect is exactly the same. For the time being, I leave the converter disconnected and short circuit, so there is at the moment no harmonics spread out in the distribution grid. You can see that the load has a poor power factor, and the utility would not accept such a load without penalties. And therefore the first step is to compensate the reactive power of this load, and I do that by means of a capacitor. So I switch on the capacitor now, and what you can see is that the power factor of the load is immediately improved. I disconnect again the power factor correction, and instead I connect now my converter. I remove the short circuit, and what you can see now is the impact of the harmonics of the converter on the source of the distribution. You see now the harmonics from the converter. This is this green highlighted curve, and you see how these harmonics affect also the current of the source. And you can see down there 50 Hertz, and then you have 250 and 350 Hertz. So the harmonics feedback into the source are relatively moderate. But as we have learned before, I need to compensate the reactive power which is produced by my load, and therefore I have to switch on the capacitors. And as soon as I switch on the capacitor, I see that the harmonics increases in the distribution network, and that would never be accepted by the utility. You can see that the harmonics is even bigger than before. I switch on and off again. You see, without capacitor, moderate harmonics; with compensation, large harmonics. And this the utility also would not accept.
If you want to build and run your own simulations, go to www.ecsb.ch. There you can build your own networks and run simulations. Very easy, very simple, very good for training purposes.
So instead of a capacitor bank only, I would install a filter. I would leave the value of the capacitor as before, so around about 100 microfarad. But instead of connecting it directly to the bus bar, I would connect it by means of a reactor to the bus bar. And before I do so, I would like to find out the value for this reactor. So the first filter I would install would just compensate the third harmonics. This is this 250 Hertz, and let's now design such a filter. Here is now the filter. I have these 100 microfarads down there, and in series I have now this reactor, and I would like to tune the filter so that the resonance frequency of the filter is a little bit below 250 Hertz. So I have to adjust the reactor so that I will land on a little bit below 250 Hertz. I assume this is now correct. So let's see what is the value of the reactor. It is 4.8 millihenry. I go now back to my main circuit, and I replace the short circuit here by a reactor with a value of 4.8 millihenry. So the reactor is now in the circuit, but for the time being it is short circuited for demonstration purpose, and as soon as I open the short circuit, the reactor becomes effective, and look at the difference in the harmonics. So now I still have these large harmonics, especially the third one is very large. And I open now, sorry, the fifth one. And I open now the short circuit of the reactor, and you see now the third harmonic is close to entirely removed. So this is a huge improvement compared to before. But even though I have now a filter and not only a capacitor, the effect of the capacitor on the reactive power compensation is still totally there. And in order to demonstrate so, I remove the source of harmonics. So there is now no harmonics anymore, and you can see that even though I have a filter, the reactive power compensation of the filter is still there, because at 50 Hertz the reactor has virtually no impact. At 50 Hertz you see basically only the capacitor. So this is the proof that the filter also takes care of the reactive power compensation. So far I have a filter which takes care of the fifth harmonics only. What about also looking at the seventh harmonic? So I would go for a two-branch filter. So I have now my two filters in parallel. The capacitors are still as before, so 50 micro, 50 micro. But the reactors have now two different values, and I have to tune the value so that one of the filters takes care of the 250 Hertz, so that reactor has to be tuned accordingly. Just below 250 Hertz, that's what it is more or less. And the second one, I take it to close to 350, a little bit below. So this is what I have now. That's a little bit, should be a little bit below the frequency I want to remove. So the second reactor would now have a value of around about 4 millihenry. In the main circuit, I add now the second reactor. The first reactor would then be around about 8 millihenry, as we have seen before. The second reactor would be around 4.1, 4.2. Let's connect now again our source. So you can see now that my harmonics have been close to entirely removed. So if I remove the filter, you see the harmonics, and if I switch on the filter, I see that the harmonics on the source have close to completely disappeared. So this is a perfect filter, which at the same time also takes care of the reactive power compensation. If you want to build your own circuit and learn, go to the online simulator, which is available on the following web address.